but the underlying principle is very, very simple. So to make things flexible, you just need to make them thin enough. So let's say a aluminum block is very rigid and not flexible at all. But if you reduce the thickness to like microns, then the aluminum foil becomes flexible. And in semiconductor, if you have ever touched a silicon wafer, it's very rigid and brittle. But when you fabricate silicon devices and reduce their thickness to nanometers, you will see they become like ribbons that can, be flexible. So, the takeaway here is, you just want to make sure your material is thin enough so that it becomes flexible. Then how do we make things stretchable? Metal itself is not very stretchable, but if you make a metal spring, it becomes highly stretchable. Similarly, when you make silicon structures, you can have this kind of wavy structures. Then you can make the structure stretchable by having some making them buckled, right? And this is another photo of a bioelectronic device where they have gold traces. So gold itself is not very stretchable, but by having these serpentine traces or zigzag traces, when you stretch, the structure will also stretch with the substrate. So in this device, we essentially have gold traces patterned on silicone elastomer, so which is stretchable. So when you stretch, the gold traces will stretch with the underlying substrate. So two messages here. Make them thin enough to be flexible and make them wavy to be stretchable. Okay, yeah, that's how we design electrodes for ECG devices. You will see that in just a second. So we want to optimize electrode skin interface. So, but what is really the skin electrode skin interface? So our skin consists of epidermis, dermis, and hypodermis. So